Hi, this is Matthew Updike, and this is Purdue Aerial Robotics Technical Design Review. I've been on the team for 4 years, acting as the captain, and I'm a senior in aerospace engineering.
Hi, I'm Eric O'Keefe. I'm a senior in mechanical engineering, and I've been on the team for 4 years. I am the chief engineer and lead of the competition team.
I'm Andrew Swanbeck. I'm a senior in mechanical engineering and computer engineering. I've been on the team for 3.5 years, and I'm the chief systems engineer.
I'm Cameron Johnson. I'm the optics and avionics lead, and I'm a sophomore in electrical engineering technology.
My name's Corey Auerbach. I've been on the team for 2 years. I'm a sophomore in aerospace engineering, and I'm the airframe lead.
Hi, my name is Evan Cam. I'm a senior in mechanical engineering. I've been on the team for 2.5 years, and I'm the airdrop lead.
I'm Dean Smith. I'm a junior in mechanical engineering, and this is my 3rd semester on the airdrop team.
My name is Aiden Bilger. I'm the integration and test lead and safety pilot, and I'm a freshman in aerospace engineering.
Hi, I'm Leonard Jump. I'm a senior studying aerospace engineering at Purdue. I'm currently GNC lead, and I've been in lead now for 2 years.
My name is Mahesh Mathun. I'm a sophomore in computer engineering. I've been part of the team for 1.5 years, and I'm the ODLC lead.
Guapo is our 2023 competition UAS, designed, built, and tested by 50 Purdue students in over 10 majors. It is our largest ever manufactured aircraft with a wingspan of 13 feet and a weight of 48 pounds. Manufactured with over 90% carbon composite materials, it maintains a lighter internal structure and stronger overall design. Guapo has extremely redundant communication, hardware, and optics, which allows us to achieve all components in this year's mission.
So back in September, our team went through the rules and used our past experience to create a list of hundreds of L1 through L3 requirements that would inform the design of our aircraft as a whole. And I'll focus on a couple of the key requirements here and go through the rationale for why we chose them. So we knew from the rules that we'd need a range of at least 12 miles based on how far we might have to fly. So we targeted 15 miles for some buffer, and we are pleasantly surprised to have 20 miles of range so far with our current batteries. We targeted a slow cruise less than 18 meters per second because that's the edge of our motion blur for our cameras for the recognition task. And we targeted 15 meters per second and have hit that value. The weight, we have to be under the FAA 55 pounds. We targeted 45 and we are slightly overweight at 48. And for ODLC, we figure with 3 out of 4 characteristics correct, we can do statistical inferencing and get all 5 of those targets recognized every time. So we're targeting 90% accuracy, but we think 78%, which we're at, will do the job, and we'll be tuning it in the coming month.
Our 2023 UAS package is comprised of 3 main subsystems. We have our ground control station, as well as a ground control station operator, which analyzes vehicle telemetry. We have our flight platform, which includes our physical UAS, as well as a safety pilot. And third of all, we have ODLC, which is mostly computers and algorithms. One of the new features in our aircraft this year is off-board position control. And what this allows us to do is have more flexibility in our mission due to dynamic path planning. We also have a fully autonomous ODLC pipeline with the option of a manual override from an additional operator in case there was to be failure. Our UAV can be set up and operational just under 15 minutes and has a flight time of 40 minutes as well as a breakdown time of 5 minutes, putting us well within the time limits of our mission.
The avionics board houses our Pixhawk, which communicates directly to our guidance, navigation, and control. It also allows us to reroute wiring so that we can easily wire the plane. The avionics team had to build many custom boards in order to fit our needs on Guapo. The first board we built was a power distribution board. Many of the components and many of the systems on the Guapo need to have a specified voltage. The power distribution board will receive an input voltage of 12 volts and it will output other voltages based on what those systems need. Guapo is equipped with a 23 megapixel GoPro Hero 10 that provides our team with 5.3K image resolution.
GoPro captures 5.3K video frames. Each frame is then sliced to 640 by 640 images. each of which are passed to a UO object detection model that identifies the target and determines its shape. Each target is then cropped and passed to a unit segmentation model that segments the target to shape and character. The mean RGB value is then calculated for both the shape and the character, and this value is passed to an RGB color classifier that determines the colors. Finally, all these values are used as inputs to a decision calculator that determines whether to drop the payload or not.
So our payload uses an interlocking mechanism that allows for easy access to the water bottle, and our parachute is spring-loaded. It is released using a time delay computer that begins counting upon the release of this limit switch. So here's an example.
The aircraft has 3 different modes of communication with the ground station. Our first mode is a 2.4 gigahertz RC radio connection. This allows the test pilot to take over in the event of an emergency, as well as for takeoffs and landings. The second mode of communication is a 915 megahertz telemetry radio. This allows the aircraft to connect to the ground station, push telemetry, as well as receive different missions or different waypoints as we need to fly them on the aircraft. This gives us a full connection between the Pixhawk and our Cube ground control system on the ground. Finally, we have a 2.4 gigahertz data link. Right now we're using omnidirectional antennas on the aircraft and then a directional patch antenna on the ground. This allows us to pull our images from the aircraft, crop them, annotate them, and then push them back up to the aircraft.
Guapo has a 13-foot wingspan with a NACA 6415 chosen for its stall characteristics, featuring a polyhedral in the middle of each wing. Having this polyhedral in the middle allows us to use the same mold for both sides. We can make more with less molds. The control surfaces are split right in the middle of the aileron. This allows us to make custom flaperon mixing within the controls to allow for an easier slow flight capability. As we move to the back of the aircraft, we have a wide tail featuring a 60-inch span on a 20-degree incline. We also have a motor, 380 kilovolts, driving a 22-inch propeller. As we move to the front of the aircraft, we begin to see those propulsion batteries inside of the fuselage. These propulsion batteries are 6-cell, 1,200 milliamp hour each, and this provides up to 15 kilograms of thrust. At our cruise speed of about 15 meters per second, we can get about 40 minutes of flight with these 2 batteries alone. The landing gear is fully custom, allowing for high damping on a hard landing. The aircraft is fully carbon fiber with plywood internal structures. The fuselage features a core mat material to allow a stronger build, while the wings have a much thinner twill layer.
For autopilot, we're using a Pixhawk Cube. We developed our own breakout board Pixhawk Cube to allow it to interface with other devices and not be restricted to just the default breakout board provided by the Cube developers. On the Cube, we're running PX4. This allows us to both run mission or manual flights, as well as running off-board missions where off-board position set points are being sent to the Pixhawk to then fly our plane around. For the off-board computer, we're running a ROS node on Xavier that sends positions such as latitude, longitude, altitude waypoints to the Pixhawk, which then in turn, through the Pixhawk control library, guides the plane towards its destination. This allows us to run autonomous missions that can dynamically change as an environment around an airplane also changes.
Our ground control station features 3 different monitoring stations. One of them is our mission control station, the second is onboard system telemetry, and the third shows images of the aircraft in live time.
In the event that our aircraft encounters another aircraft in the airspace in front of it, we're able to detect it using a millimeter wave radar sensor from Texas Instruments that returns a point cloud of the space in front of it. We're able to find that obstacle using a point cloud returned from the sensor and then dynamically path plan around the obstacle until it's clear, and once we're clear, we can then resume the mission from the ODLC waypoints that we've plotted and then our standard path planning algorithms.
So during the course of the design process, we considered a lot of different alternatives on our different sub-teams. So some of the important configuration options we had were VTOL, vertical takeoff or landing, tractor, or a pusher. And we ultimately decided that a VTOL, while it has a lot of key benefits, such as being able to hover over our airdrop area and being able to take off vertically for the other runways, that this was not worth the design complexity and had far too high of a risk. So we decided to opt for a classic fixed-wing design with either a tractor or a pusher. And we decided ultimately that a pusher would be better because we could put a camera in the front and balance the CG better in the back with a pusher and also have less disturbed air for our optics. For airdrop, we considered several different designs, the first of which being a glider. And this glider would be controllable and steerable all the way down to the target. But this ultimately was decided to be too weight intensive and size intensive for our airframe. So we decided to go with a parachute solution. Our two options were an immediate parachute drop or delayed parachute drop. And through testing and math, we determined that the immediate parachute drop would not have a required accuracy of 15 feet. And so we decided to opt with a delayed drop that would drop out of the aircraft and around 40 feet, some safe distance, would deploy a parachute.
Risk mitigation and safety are a key part of our goals here at the Purdue Aero Robotics team. We exercise safety and risk management anywhere from wearing safety glasses and respirators when we need them, to designing our testing plans around that, which is especially critical when we're testing out new hardware. We also try to mitigate risks by testing out our technology on technology demonstrator aircraft that are cheap to replace and much easier to replace than our full-scale competition aircraft. Another part of our safety is that we always have an RTH feature built into our aircraft, so at any point if we were to lose comms or signal, the aircraft would automatically land itself back at the runway.
To evaluate the performance of the GoPro and other cameras, we had to come up with a variety of different testing methods. The first testing method is to evaluate how the GoPro handles very fast speeds of the plane. First, we flew the GoPro at 15 meters per second at about 100 feet up in the air. After doing multiple passes of different objects and of different sizes, we felt that the GoPro passed this test with flying colors. To test the color accuracy of the GoPro and other cameras, we had to test them in different lighting conditions. These lighting conditions varied a lot, from sunny days to rainy days to cloudy days. Additionally, we had to test them at different times of the day. Unlike other cameras, the GoPro passed all of our tests, and that's why we decided to incorporate it into Guapo.
So far our team has conducted 87 tests, of which 65 of them have landed within our ideal zone of 15 feet from our target. In that time, we've had no mechanical failures with the dropping mechanism, and we've only had one mechanical failure with the parachute release mechanism, which caused for a redesign, and since that redesign, we've had no other mechanical failures.
Some statistics about the radio connection between the aircraft and the ground station is all about range and bandwidth. So our range is up to 12 miles for our RC connection. We get 30 kilometers of range for our 915 megahertz telemetry radio, and then we get 6 kilometers worth of range for our Wi-Fi data link, all pushing 20 megabits per second or faster for the Wi-Fi data link, allowing us to receive images and push images as we go instantaneously. The telemetry connection using the XBP9X 915 megahertz radios experienced between 3 and 7% packet loss during all ground and flight testing.
Our flight time of 40 minutes far exceeds anything required by the competition, allowing us to fly about 20 miles as compared to the 12 miles of waypoints. Our slow flight characteristics allow us to have a very small turn radius, well under the 125 foot required. We also experience very high angles of climb and descent safely with the aircraft due to our high power. We've also experienced through testing a very high range, well exceeding 1,000 feet, while over 75 feet above the ground.
To verify our autopilot performance, our team is conducting multiple autonomous missions. Each of these autonomous missions involve flying a series of waypoints, surveying an area, and making sure to stay within a safe flight boundary. We've conducted about 30 or so of these missions. Each of these missions have about 30 waypoints each. On average, we hit our waypoints pretty dead on. However, we do have a slight give. Our average miss is about 8 feet. We have about 30 seconds or so of each flight where our pilot is in total control of the aircraft.
The obstacle avoidance system on board the aircraft performed exceptionally as it was tested extensively on the ground and 5 times during flight. All 5 times, the aircraft detected and avoided the obstacle, resulting in a 100% success.
Our team has conducted 4 end-to-end mission tests in which we fly 12 miles of random waypoints, set up a target drop zone, deploy our payloads, and then land safely. We expect to use 2 to 3 overall operators during the competition and to hit 3 to 4 of the target areas. Our simulated mission scores are on average 70%, and we expect 85% total score at the competition.
The aircraft now is in mission mode, autonomous. We're flying at 35 meters above ground level, so a little bit over 100 feet. As we approach our first waypoint, we're going to make a left-hand turn.
We hope this presentation has given some insight into our technical design, testing methods used, and our predicted outcomes. Guapo is our most ambitious and safest aircraft to date, and we cannot wait to show it off to the world at this year's SUAS competition. We'd like to present an extended thank you to our corporate sponsors, those organizing the competition, and our faculty advisor, Dr. Sundaram. Boiler up.